Hey everyone, today's lesson from Unit 2.1 is our very last lesson in this unit. It's notes number 11, and we will be taking a look at medians and altitudes of triangles. A median of a triangle is a line segment from a vertex to the midpoint of the opposite side. So let's take a look at a triangle. I'll just show you one median to start with. So in this triangle, if we are given information that this point was the midpoint of this side, either through markings or written given information, if we connected this vertex to that midpoint, this line segment that we'll call AM would be an example of a median. Every triangle has three medians, and we're going to take a look at what these medians look like in an acute triangle, a right triangle, and an obtuse triangle. So notice that in each of these three triangles, one median is drawn for you. And what I would like you to do is take your ruler, and I can't use a ruler on the iPad, so I'm going to draw mine freehand. But you're going to take your ruler and you're going to connect each remaining vertex, so I'm going to start with this vertex right here, and connect it to the midpoint of the opposite side. So that's this point over here. So I've marked in the midpoints for you, so all you need to do is line them up with your ruler and connect the 2 points. So that's the second median of this acute triangle, and then the third median would look something like that. Okay. So now take a look at the right triangle. So connect this point at the top with the midpoint of the opposite side. Connect this vertex down here with the midpoint of that side. Again, yours should be a lot neater since you're working with your ruler. In the obtuse triangle, connect this vertex with the midpoint of that opposite side, and connect this midpoint with that vertex. And again, we have our third median drawn for each of these triangles. So three medians in every triangle, and you should notice something about these medians. Okay? If you take a look, the three medians always meet at a single point, if you did it neatly enough. Okay, so again, if you used your ruler, then you should see that those three medians do meet at exactly one point. So we can say that they meet or intersect at a single point. So when something like this happens in a triangle, when we have three or more lines that intersect, their intersection is called a point of concurrency. So it's spelled C-O-N-C-U-R-R-E-N-C-Y, concurrency. Concurrent means happening at the same time, so point of concurrency is where the lines all intersect. So when we have points of concurrency, they're often given a special name. In the case of the medians, where the three medians meet in a triangle, it's called the centroid. And that's hard to read, so let's try that again. It's spelled C-E-N-T-R-O-I-D, centroid. So next we're going to talk about a theorem that relates to the centroid and the medians of a triangle. It's not actually called the centroid theorem technically, but I just thought I'd give it that title. The medians of a triangle intersect at a point called the centroid that is 2/3 of the distance from each vertex to the midpoint of the opposite side. Okay, so it's a little confusing. So let's draw a triangle. And let's go ahead and put in the medians. So that will be a median if these two segments are congruent. This is a median if these two segments are congruent. And this is a median if these two segments are congruent. So again, median goes from vertex to the midpoint of the opposite side. So what the centroid theorem says is that when these medians meet at this centroid, this single point in the middle of the triangle, then this centroid is 2/3 the distance from the vertex to the midpoint of the opposite side. In other words, each of these line segments, each of these medians gets divided into two parts, a longer part and a shorter part. The part from the vertex to the centroid is going to be longer, and that's always 2/3 of the entire length of the segment. The part from the centroid to that opposite side will be 1/3. So in other words, if we had a line segment, and let's just say, for instance, this median had a length of 3, then this distance would be 2, and this distance would be 1. Because this is, if the whole length was 3, this is 2/3 of 3, and this is 1/3 of 3. Okay, we're going to practice this with a few problems. Okay, in our example, we're given triangle DEF with midpoints J, H, and G. So first, take your ruler and draw each median. So connect D to H, connect F to G, and connect E to J. Again, using your ruler will make it even more precise than my picture here. So mark the centroid with the letter K. So K is right there, where all three medians intersect. Okay, so now we're going to use that centroid theorem to answer each of these questions. So in here we're asked to find, or to compare, the length of KJ to the whole length of EJ. Remember that the medians, when they intersect at the centroid splits them all up, so each of these is split into the fraction 2/3 for the longer piece, 1/3 for the shorter piece. So we would say in here that KJ is equal to 1/3 of the length of EJ. Working with another median, line segment DK, and I'll highlight that in blue over here, that's equal to 2/3 of this whole line segment. So 2/3 of DH. For our last median, we're going to compare line segment FG, that's that whole segment, to line segment KG. So this is 1/3 of the whole thing. Then FG has to be equal to 3 times the length of KG. So 3 times this length will equal this entire length. Okay, I'm going to clean this up a little bit, and then we're going to plug in some numbers. Okay, my attempt to erase things didn't work, so we're going to try something else. In part E, it says if FG is equal to 24, that's this, again, whole line segment from F to G, then KG is going to be 1/3 of that. So KG equals 1/3 of 24. So just take and divide 24 by 3, and we end up with 8. For the next question, we're looking for the length of lines. We have line segment JK, and that's equal to 9. And we want to find the length of JE, this whole entire line segment. Well, if JK is 9, and that's 1/3 of the whole segment, you can take and multiply it by 3, and that will give us the length of line segment JE. 3 times 9 is 27. Another approach to this is to take JK and double it, and that's going to be KE. When I take 9 and double it, I get 18, and then add them together to find the whole length of line segment JE. Finally, for the last one, for part G, it says if DK is equal to 8, then DH has to be equal to what value? I find it easiest to remember that DK is the longer segment, so that's 2/3 of the whole. So that means that KH has to be half of that, or 4. And together, they would add up to 12. So the length of DH is 12. In addition to medians, another special line segment in a triangle is an altitude. An altitude of a triangle is a perpendicular segment from a vertex to the opposite side. So we're just going to spend some time sketching these altitudes in these triangles. And what you need to be able to do on the homework and on our quiz and on the exam is just recognize what an altitude is in a picture. So in an acute triangle, if we want to draw an altitude, we can use the ruler and line up the marks on the ruler with one of the sides of the triangle, and then you want to connect the vertex to the opposite side so that we get a right angle. So every triangle has 3 altitudes, so I'm going to draw in all 3 of them. You notice in this acute triangle, the 3 altitudes meet in the center or inside the triangle, not exactly in the center. In our right triangle, we're going to do 3 different cases with it. If I want to draw the altitude from this vertex right here, it would be perpendicular to the hypotenuse of the triangle, like that. In the right triangle next to it, where it says right triangle number 2, do you see how line segment AB is perpendicular to BC? AB is actually an altitude to line segment BC. It says altitude in there. We'll try that again. So AB is an altitude. We can say from A to line segment BC. Okay, our right triangles. This is the third one. Line segment BC is also an altitude. Okay, so remember every triangle has 3 altitudes. Next, in an obtuse triangle, this is where it gets a little trickier. For drawing an altitude from this vertex, perpendicular to the opposite side, that's not too hard. You can do that easily with your ruler. But if we go to obtuse triangle number 2, if we try to draw an altitude from this point, it has to be perpendicular to the opposite side. So notice that it cannot happen or cannot be drawn inside the triangle. If we were to draw an altitude from that point to the opposite side, it would have to come down this way. So what you need to do in the case of an obtuse triangle is extend that opposite side, then drop in your altitude. So sometimes the altitude of a triangle can occur outside of the triangle. Okay, if we try this again in obtuse triangle number 3, we want to draw an altitude from this point in the lower right hand corner. Again, I can't draw it inside of the triangle so that it's perpendicular to that side. So what we need to do again is to extend this opposite side. Just make it a dotted line. You can use your ruler for that. Go back to this vertex, and now you can draw your line segment so it's perpendicular to the line that contains the opposite side. Okay, so again, in an obtuse triangle, 2 of the altitudes are drawn outside of the triangle. Okay, next, take a look at the CYU. Give those problems a try, and then check your answers at the key, and as always, speak up if you have any questions.